Welcome to the deep dive. Today, we're taking a really fascinating turn into a corner of mathematical optimization that most people, well, even people in the field, have kind of dismissed.
Yeah, written it off as an academic footnote.
Exactly. We're talking about the ellipsoid method.
It's an algorithm with, let's be honest, a terrible reputation. When practitioners hear ellipsoid method, they usually think slow, clunky, and, obsolete.
But our deep dive today is going to challenge that completely. We've pulled together the history, the technical details, and some really modern applications to show you why this method, despite its perceived slowness, might just be the secret weapon for solving problems of, well, mind-boggling complexity.
That's right. Our sources, they all point to a truth that goes way beyond just the geometry of it all.
We're diving into the heart of the algorithm. We're not focusing on the shrinking ellipsoids, but on the hidden computational genius at its center, what's called the oracle.
And our mission really is to prove to you that for certain classes of problems, this supposedly dusty old method is absolutely indispensable.
Before we jump into the mechanics, though, you mentioned something about the philosophy behind it.
I did, yeah. The whole process, it just perfectly embodies this spirit of elimination. It's actually best captured by that famous quote. When you have eliminated the impossible, whatever remains, however improbable, must be the truth.
That's Sherlock Holmes, of course.
Precisely.
Yeah.
And that idea, it perfectly mirrors the ellipsoid method's approach. It's a search that's based entirely on proving and eliminating huge regions of impossibility.
Until only the truth remains.
Until only the truth remains. But to appreciate the magic, we first have to tackle the baggage.
Okay, let's do it. Let's review the common wisdom about the ellipsoid method, or EM, because when it first came out, it caused a huge sensation. But today,
Yeah, most people see it as a theoretical relic.
useful only for proving complexity bounds, right?
Right. It's seen as slow, impractical, especially when you put it up against the modern workhorses, the interior point methods. And that sensation you mentioned, that was back in 1979. A mathematician named Leonid Khachiyan used the EM to prove that linear programming LP, which is the bedrock of optimization, was polynomial time solvable.
A massive theoretical breakthrough. It changed the entire field of computational complexity.
It did. But almost immediately after, for any kind of large-scale production use, it just got pushed aside.
And the source of that dismissal, it really lies in the complexity rating itself, doesn't it? The criticism is always hyper-focused on the number of iterations it takes.
Correct. Its iteration count complexity is 202 else, and that 202 term. That's a killer. It means the complexity grows quadratically with the dimension no of the problem.
Which just looks horribly inefficient for anything big.
Exactly. And just for the listener, that epsilon, the epsilon, that's just the precision you want for your answer. The smaller the epsilon, the more you have to iterate.
And another key criticism is its inability to leverage sparsity. What does that mean for someone who isn't, writing matrix equations for a living?
So in optimization, sparsity just refers to how many zeros are in the matrices that define your problem. Most real-world problems are super sparse. Most of the entries are zero.
Okay.
And modern solvers, they are fantastic at exploiting that. They can basically ignore the zeros and solve things much, much faster. The ellipsoid method, at least in its traditional form, doesn't really see that structure, so it looks sluggish.
Okay, so the conventional wisdom looks at that Endowie-2 term and just says, forget it, too slow.
Mm-hmm.
But that's where our central shift in perspective comes in. We're saying that critique focuses on the wrong part.
The wrong component entirely. The search mechanism itself, sure, it might be quadratically slow in mild hours, but the real power, the true intelligence of this thing isn't in how the ellipsoid shrinks.
It's in how the cut is found.
That's it. The efficiency is purely a function of the oracle.
So let's define this separation oracle. It sounds like something out of Greek mythology.
It does, but it's just an algorithmic procedure. Its job is elegantly simple. It is a subroutine that is only responsible for answering one single local query about the current test point, which we'll call sex1.
And what's that ultimate question it has to answer?
Is the test point $6 in the feasible set dollars? That's all. It's only ever asked about the local feasibility of one single point.
It has two possible replies.
Two possible replies. The first one is assertion. If 6 rays is feasible, then we know we're either done or we update our objective value and, we keep going.
And the second response?
The second, and this is the crucial one, is separation, or the cut. If 6 rays is not feasible, the oracle have to return a hyperplane. Think of it like a flat geometric slice. that proves 6er is infeasible.
And that cut is what slices a piece off the ellipsoid.
It slices it away from the solution space.
This is where my mind was blown, because the oracle's brilliance is that it lets us solve problems that have potentially, infinite constraints.
An infinite number of rules that define the boundary of the feasible set, and you never ever have to list them.
That's unbelievable.
It's the ultimate form of, let's call it, computational laziness,
Hmm.
but leveraged in the most intelligent way possible. It doesn't need to check 10,000 rules. It just has to find one single violated constraint at a time.
So the problem formulation is implicit. We don't write down all the constraints, we just need an algorithm, the oracle that can find one if we ask it to.
Find a violated one on demand. That's the whole game.
Think about that. A problem so big, the rulebook could fill a library. The oracle doesn't read the library. It just looks at where you are right now and instantly finds the one rule you broke.
So to really drive this home, we have to look at this in practice. These aren't toy problems. We're talking massive, real-world complexity.
Let's get into the case files. 3 examples that show just how clever this oracle has to be.
Okay, first up, robust convex optimization. The challenge here is finding a solution, let's call it $6, that has to stay feasible and optimal not just for one set of parameters, but for all possible values of some parameter dollars inside an uncertainty set CARTI.
So if that set Q is a continuous range, like say all temperatures between 20 and 30 degrees,
You're facing an infinite number of constraints, one for every single point in that range. You'd be writing them down forever.
so what's the oracle's secret trick?
It doesn't try to check them all. For the current test point 6 point, the Oracle solves a little secondary optimization problem. Its only goal is to find the single worst case parameter, we'll call it the max, that causes the biggest violation at 6 equal.
So it's actively looking for the one scenario that makes the current solution look the worst.
That is its whole focus. And it uses that one, single mouton, to build and return the cutting plane. For instance, if you're robustly maximizing profit, the Oracle doesn't care about average market conditions.
No.
It instantly identifies the combination of the lowest possible price you could sell for and the highest possible cost for your inputs. That one worst case scenario, that's what generates the cut.
Okay, here's my critical question on that. If the oracle has to solve a whole other optimization problem just to find that key max, how do we know we're saving any time? What if that subproblem is just as hard?
That is a fantastic, crucial question. The reason this works is that the subproblem, while still optimization, is usually a convex maximization over that uncertainty set QA. If QA has a simple shape like a sphere or a box finding, that worst case QMAX often has a simple closed form solution.
So it can be solved trivially.
Or very, very quickly, independent of the size of the original problem. The trick only works if finding the worst case scenario is easy.
That makes sense. It's trading complexity in this search for simplicity in the check.
Precisely. Let's move to case file ZO2. Semi-definite programming, or SDP. This stuff is vital in, control theory, structural engineering.
So the challenge in SDP is finding a vector $$ that makes a matrix function positive semi-definite. For the listener, what does that actually mean for a matrix?
It means that if you take any non-zero vectors dollars, and you do the calculation vi t f x vi thou, the result has to be greater than or equal to 0.
And that has to be true for all possible vectors, every single one. And since there are infinitely many possible vectors, we are right back in infinite constraint territory.
So what's the oracle's trick here?
It's incredibly subtle. It uses what you could call a lazy decomposition check. It tries to do a standard matrix decomposition, like a Cholesky or LDLT decomposition, on the matrix 5xe.
What's a good analogy for that decomposition process?
Think of it like peeling an onion, layer by layer. The decomposition checks the structural integrity of the matrix. If the matrix is good, if it's positive semi-definite, the whole onion peels cleanly.
But the oracle is lazy.
The oracle is lazy. It stops the very first sign of trouble, the first rotten layer.
The moment the process would require, say, taking the square root of a negative number, that's the one. If the decomposition fails at some row, say row p dollars, the oracle doesn't just stop. That failure point gives it the raw materials to construct something called a witness vector, vivalor.
A witness vector? That sounds like something out of a crime scene.
It basically is. It's the proof. That single vector $5, which it gets directly from the failure, is the mathematical evidence that vi-t f eval v is less than 0.
So it's the specific vector that proves the matrix is bad.
And that's the vector it uses to generate the cut. And what's amazing is the efficiency. The check in generating that witness can take as little as 1 p$3 operations, where ballers is the row where it failed. So if it fails early, it's incredibly fast, no matter how huge the full matrix is.
That is computationally brilliant. It only puts effort into the exact part of the structure that broke the rule. Okay, so from continuous constraints to exponentially large discrete ones, case file Zo3, parametric network optimization.
Right. This is about making sure no negative cycles exist in a graph.
The constraint being that the sum of weights around any closed loop, any cycle, has to be non-negative. But in a big graph, the number of possible cycles can be astronomical.
Exploding exponentially. You could never list them all.
So how does the oracle, which we've seen slicing up continuous spaces, handle this?
It delegates. The Oracle just runs an existing, very efficient negative cycle detection algorithm, something like Bellman-Ford, on the network. It doesn't try to invent a new way to solve the problem.
It just leverages known graph theory.
Exactly. And if that Bellman-Ford algorithm finds a path where the costs just keep spiraling downward,
That path is the violated constraint.
that's your violated constraint. If a negative cycle, let's call it $2, is found, that single cycle provides the rule that was broken. The total weight of that specific cycle is what it uses to construct the separating hyperplane.
It's just incredible how flexible this framework is. We've gone from infinite continuous constraints to infinite vector constraints and now to exponentially many discrete ones.
And its versatility, it goes even further. For instance, into discrete optimization, where your variables have to be integers. Think scheduling problems, or where to put a new facility.
How does it generate a continuous cut based on a discrete rule being broken?
It's a neat two-step process. The Oracle looks at the current continuous center point, $60. If that point is infeasible, the Oracle then finds the closest discrete solution, which we can call $6.
So the nearest integer assignment.
Right. Then it checks if that discrete point, $6, violates any constraint. If it does, the cut is generated based on the rule that was broken at $6.
So it tests the water at the continuous center, and if it's looking bad, it checks the nearest safe harbor, the discrete point, and then generates a cut that pushes the whole search space away from that problematic integer solution.
That is a perfect analogy. And this technique can handle some really tough, non-convex discrete constraints. But wait, there's more. The Oracle itself can be upgraded.
We talked about a single cut.
Right. But in some fields, like FIR filter design, which is about designing electronic signal filters, we can get even more aggressive. The sources mentioned parallel cuts.
Parallel cuts.
Yeah. For some problems where the boundaries are predictable, the Oracle can sometimes return two separating hyperplanes at once. This parallel cut basically carves out a much bigger slice from the middle of the ellipsoid.
Which speeds up convergence a lot compared to just one cut.
Significantly. And finally, even the supposedly clunky implementation of the method has been refined. It's not just running brute force geometry in the background.
Right, the details matter.
They're critical. The standard update for that ellipsoid matrix, POLARs, is Noller's operation. That's where that nasty complexity factor comes from, if you have to recalculate a huge matrix every single time.
The cost adds up fast, so how do the smarter implementations get around that?
They separate the function of the matrix. They split the matrix dollar into a simple scalar volume factor, let's call it kappa, and a shape matrix. So you have PLP aka QDOL.
Wait, why does splitting the volume from the shape save operal operations?
Because the goal is to shrink the volume while maintaining the right shape. By separating volume, kappa, from shape, you only have to update the simple scalar kappa frequently. You avoid doing a costly full matrix multiplication on the big shape matrix kappas in every step.
So the really heavy lifting is done less often.
Much less often.
Yeah.
The updates can be structured to save thousands of floating point operations per iteration, and you might only need one square root for the whole step. The math is really elegant.
This just proves that the perception of the ellipsoid method being inherently slow is, well, it's just false. Its ultimate speed depends entirely on the oracle.
Absolutely. The new truth, what we should take from this deep dive, is that the ellipsoid method is not a slow competitor to interior point methods. It is their essential companion.
Interior point methods are phenomenal when your constraints are explicit, when you can list all the rules up front. But the EM is the heavyweight champion for problems where the constraints are implicit.
Where the rules are infinite, or uncertain, or exponential, its power is transforming a seemingly impossible problem into just a sequence of smaller, tractable feasibility checks.
And that brings us to the most important realization.
We have to stop using the old metrics.
The right question to ask is no longer, how fast is the ellipsoid method?
The bottleneck is outside the ellipsoid. The real measure of success for these incredibly complex problems is about innovation in those subroutines.
So instead, the driving question for modern optimization is this: how clever is my separation oracle?
That's where the engineering effort belongs. Inventing an algorithm that, at every single step, knows precisely how to find the one single worst case counterexample it needs to generate the perfect cut. And that search for cleverness, that is what will continue to unlock problems that conventional solvers can't even begin to formulate.
Something to mull over until our next deep dive. Thanks for joining us.